In 1969, NASA was responsible for the first man walking on the moon. In 2030s, NASA would like to be responsible for the first man walking on Mars. With all this hype, we would like to be responsible for sending the first interstellar astronaut to space. Hello, my name is Clarissa Olivar Magallanes, and I'm working in Professor Joel Rockman's lab under the mentorship of Pradeep Joshi and Cricket Wood. So, how will we get an organism to space? There's a group called DEEPIN, and it is run by Professor Lubin in the Department of Physics at UCSB, and is partnership with NASA. So what Professor Lubin is doing is he's creating a wafer-scale spacecraft, and as you can see, it's the size of a quarter. And its destination will be Proxima Centauri, which is a star that's approximately 4 light years away from the sun, and this trip will take approximately 20 years. But we also have another thing. So short term, we are working with Blue Origin, which is a privately owned space company, and it is owned by Jeff Bezos, and he is the CEO of Amazon.com. And we're sending it up on the New Glenn, which will enter low Earth orbit and last approximately 5 minutes. So, picking an organism. As you can see, this worm is called the C. elegans, and the reason why we pick C. elegans is that they're heavily studied. They have similar organ and nervous system to humans, as this picture demonstrates. They are capable of associative learning, and associative learning is the process in which a new response becomes associated with a particular stimulus. And the main reason is they may be placed into suspended animation, and this is a requirement for long-term space travel. And suspended animation is a state in which life in a body is temporarily stopped or slowed down. So, C. elegans share similarities to humans, and that's why we chose to send them specifically to space. So we want to study their growth, their development, their behavior, neural activity, and their reproduction. So how is suspended animation achieved? We are going to be freezing them, and to do exactly will be frozen. So the C. elegans has 4 larval stages of development between the egg and the adult, and we're picking L1s because L1s are empirically known to freeze the best. So the problem, however, is that it takes approximately 30 minutes for C. elegans to begin moving after being thawed, and like I said, for the Blue Origin trip, we only have approximately 5 minutes. So goals. Long term is we want to determine the effects prolonged space travel has on physiology and behavior of the C. elegans. Short term, however, is we want to limit the time for C. elegans animation to 1 minute for the Blue Origin trip. And we want to determine if C. elegans are able to retain memory after recovery from suspended animation, because like I said, they're capable of associative learning. And we're going to do this by exposing them to an odor stimulus. So there's 2 methods for freezing. One is we put them in glycerol, which is done on a tube, and the other is ethylene glycol and liquid nitrogen, which is done on a membrane. And a membrane is just a piece of filter paper that allows the liquid to seep through. So for glycerol, we can thaw the solution directly onto a plate, but for ethylene glycol, we have to submerge in 10 milliliters of water and then transfer it to a plate. So what we've accomplished in terms of freezing, so like I said, our main goal is to just get freezing down to 1 minute. So we've been able to test 7 different volumes, and for the 20 microliter, we've actually gotten closest to our goal. So we're 2 seconds away. So in ethylene glycol and liquid nitrogen, there's been a lot of failure. So the only thing we've been able to see is we tried 2 different methods. So we submerged the solution instantly in 10 milliliters of water, and for the remaining 4, we submerged it in 3 milliliters of water and then transferred it to an additional 7 milliliters of water. So the only one that's been able to actually survive and prosper is the one that's instantly submerged. So we picked this method because it reduces human handling, which will be important for the DEEPIN project, which, like I said, the spaceship is just like a quarter, so there's no humans on it. So, like I said before, they're capable of associative learning. So we want to see if they're able to retain this associative learning even after being frozen. So this is a plate, and you see different stages of development, but we only want L1s because they freeze the best. So what we have to do is we have to treat it with an alkaline bleach solution, which will turn this plate into this. It dissolves everything except for the embryo, and will allow the embryo to grow up into alkanes. The next step is to train them, so we're going to put them on a plate and expose them to an odorant, and we're going to put them on a plate that either has food or doesn't have food. The next step is to assay them, and this is just a way to quantify if they have a preference towards the odorant that we've exposed them and trained them to, or the control. The next step is just to freeze them, because this is the novelty part of my project, and we have to assay them again to see how much they were able to retain. So if they're raised with food, they're naturally attracted to butadiene, And we diluted butanone and ethanol, and that's why we picked ethanol as our control. NAN3 is just used to destabilize the worms once they reach either spot. And then they're concentrated here, so they start here. And because they're naturally attracted to butanone, we expect a concentration towards butanone, and this attraction is reinforced by the presence of food. So they associate food with this attractive odorant. However, so this is reinforced behavior. However, if we raise them with this odorant that they're attracted to, and they don't have food, they associate this attractive odorant with the lack of food. So although they're actually like the odorant, they're going to associate that there's no food there, so they're going to gravitate towards the control. And this is learned behavior. And so we have to have a way of quantifying how much they were able to retain. So there's something called the chemotaxis index, which is just the number of worms of butanone minus the number of worms of ethanol all over the number of worms in the pig. And this is going to give us a number between +1 and -1. So a positive number means that they have an attraction to butanone, and a negative number means that they have an aversion to butanone. So, like I said earlier,